Good evening and welcome to the live sessions. It is 6 p.m., but participants are yet to join, so we will wait for a few more minutes before we get started. Thank you. A very good evening and welcome to week 9 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sarjan Kapil, who is a member of the faculty of the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Last week, we had started looking into wire-based additive processes, and we looked primarily at those AM technologies which used an arc as the energy source. This week, we'll be looking at those wire-based AM processes where a beam of energy is used. Typically, this beam of energy will be in the form of either an electron beam or a laser beam. So in terms of the subsystem-based classification that we have been following for the methods studied in this course, the materials which can be deposited by this process are metallic in nature, either pure metals or alloys. The flow of material is continuous. The machine kinematics can either be serial, where there are multiple links connected to each other, but only one link is connected to the end effector, or it can be parallel kinematics where multiple end effectors are multiple links are attached to the end effector. It can be a hybrid kinematic system which incorporates the beneficial features of either of these, both of them. The energy sources which you already studied are the arc based sources, which included MIG, TIG, and plasma based wire AM, and we also looked at laser. uh, we'll be starting with the electron beam right now. Electrons, as we know, are perhaps the lightest subatomic particle with a mass of only 9.1 into 10 power minus 31 kg and a charge of minus 1.6 into 10 to the power minus 19 coulombs. And so the question might arise that a particle which is so light and also has such little charge, how do we leverage it to say melt metallic materials which can have very high specific heat capacities, can have of the order of say 400 or 500 joule per kg, or melting temperatures easily in excess of 1300 1400 degrees C. So what is the property of electrons which allows us to leverage it in a AM technology? And that is its kinetic energy as shown here. As we already observed, electrons have very low mass and thus they can be accelerated to very high speeds. There's this plot here which shows how, based on the accelerating voltage to which beam of electrons is subjected, what speeds it can achieve. Uh, this black line at the top is the speed of light, which is the theoretical limit of highest speed which can be achieved by any body in our universe. And we see that for sufficiently high accelerating voltages, typically say of the order of 10 power 5 or 10 power 6 volts, electrons can be accelerated to uh, a speed which is very close to the speed of light. It will never attain a speed which is equal to or greater than speed of light, but it can get close. And it is because of this velocity which imparts momentum to the electron, uh, which when transferred to a metallic material uh, gives the necessary energy for melting and fusing it. And here, as we can see, it's very common for electrons to be accelerated to approximately two-thirds the speed of light. And as we saw in this video to the right here, what might appear as multiple electron, say beams or multiple tracks, is actually just one electron beam which is being scanned across the area to be printed. And because of the very low mass and very low inertia, it can be deflected at such high speeds that it appears to us as if there are multiple beams which are acting at the same time, whereas it is just one beam which is being deflected throughout the region of interest. Please allow me a minute. I just need to check my internet connection to ensure everything is working smoothly. So now that we know that electrons can be accelerated to great speeds, and because of this high velocity, they can uh, say transfer a large amount of momentum to the target substrate, and thus provide the energy necessary for melting and fusion of the metallic feedstock. It is useful to know how the electrons can be emitted and what are the typical electron emission techniques available to us. To emit or produce electrons from any solid state material, we have to give some minimum energy equal to the work function or potential barrier to the material. And this energy can be given in the form of heat, in which case the emission is known as thermionic emission. It can be given in the form of photon energy, in which case the emission is known as photon emission. We can have secondary electrons being emitted from target surface, which is where we bombard the target surface with a stream of electrons, and this leads to generation of more electrons, and so the name secondary electrons. And such a mechanism, of course, here as we can see, the electrons in black are the primary electrons, which when they bombard a surface lead to the production of these electrons marked in red, which are our secondary electrons. And such an emission is called secondary emission. We can also have ferroelectric emission and plasma-based emission. For metal processing such as welding, lithography, additive manufacturing, or even calculation techniques such as electron microscopy, thermionic and plasma emission are among the most popular to be used. And specifically for thermionic emission, we have Richardson's law, which relates the current density emitted from the emitter surface, J, to the absolute temperature of the emitter and the work function of the emitter. In an electron beam based wire additive manufacturing process, the primary function of the electron beam gun is to produce, focus, and deflect electrons. As we mentioned, typically either a thermionic electron beam gun or a plasma electron beam gun may be used. In both cases, first stage is the emission of these electrons. Like here we have a cathode and an anode. The anode will be positively biased, and uh, electrons which are emitted from the cathode will be attracted towards the anode. However, as we see here for this red beam, the beam of electrons did not always follow a straight path and instead they will tend to diverge. This divergence has to be controlled, and this leads to a typical beam profile which has a diverging and then converging section where it is further focused onto the region of interest where printing has to take place. A similar mechanism is also available for the plasma based electron beam gun, where again we have some uh, region for emission, and then we have the accelerating electrodes, which further accelerate and say focus and deflect the beam as per necessity. The commercial systems produced by Arkham and Siaki use thermionic guns, whereas the commercial system developed by X-beam use plasma electron beam gun. And on the bottom here, we also have a useful comparison of the two types of technologies. The current density which can be achieved with a thermionic gun is up to 10 ampere per centimeter square, whereas for plasma gun it can be up to 100 ampere per centimeter square. This it is approximately one order higher for the case of plasma gun. The acceleration voltage required for thermionic gun can be up to as high as 150 kilovolts, whereas for plasma gun we need a far lower voltage, approximately one fifth, and so it need to go only up to 30 kilovolt. The requirement of vacuum in the case of thermionic gun is high. Typically, you would require 10 to the power minus 7 to 10 to the power minus 9 bar of vacuum, whereas in the case of plasma gun, a, a moderate amount of vacuum, typically between 10 to the power minus 4 and 10 to the power minus 5 bar is needed. Thermionic guns also tend to have shorter lives. Say a typical number given here is 50 hours, whereas plasma guns can easily last for at least twice as long. And even in terms of cost, the cost of a thermionic gun is considerably higher because of the requirement of the associated high vacuum. Both, however, have overlapping applications related to melting, heating, machining, and welding. Now, as I was saying, once the electrons are emitted and attracted to the anode, they may tend to diverge instead of following, say, a collimated path, and thus they need to be focused back into a tight spot. Further, this single electron spot has to be deflected or scanned all over the region of interest on the printing plane. So we require focusing and deflection. In most EB guns, an electrostatic field is used for extraction and acceleration of the electron beam, whereas a magnetic field is used for focusing, deflecting, and correcting the beam. An schematic of such a gun is shown here on the bottom left, where we have the cathode from which the electrons are emitted. This red beam is indicative of the beam of electrons. We have a focusing electrode, which is focusing and say directing it using electrostatic forces, as we can see here. This is the region of electrostatic focusing. These electrons are accelerated because of electrostatic forces or the positive charge on the anode till the anode, and afterwards further acceleration, deflection, and correction are achieved using this magnetic field. Components of the Lorentz forces given in equation 1 are used for focusing. Lorentz forces are generated because of the interaction between the electric field and the magnetic field, and it is given here. The force generated because of this interaction is equal to Q into E plus V into B, where E is the electric field, B is the magnetic field, and V is the velocity of the electron. From the cathode to the anode, focusing is done by electrostatic forces, and further on from the anode to the required surface, the focusing is done by electromagnetic forces. In the first stage, where electrostatic focusing is dominant, the magnitude of the electron's velocity increases due to electric field, whereas in the second stage, as the name would suggest, the direction of the velocity changes while magnitude remains the same. So we are having acceleration in both these regions. In one region, the acceleration is because of change in speeds. The speed increases considerably. Whereas in the second stage, where electromagnetic focusing is dominant, uh, the acceleration is achieved only by change of direction rather than change in speed. Now, we saw how, for the case of both the thermionic gun as well as the plasma based electron beam gun, there was a requirement of vacuum. But why is it so? Because previously this has not really come up in any of the other technologies. The reason being that uh, the very light mass or the very small mass of electrons, which allows us to impart it with great momentum, also implies that it can be easily deflected if it were while traversing, if it encountered some heavy molecule or some heavy particle in its path. And so uh, we have to ensure that during their travel, electrons do not encounter any other heavier particles or heavy molecules to be able to reach the uh, target surface and transfer their momentum. Thus, a vacuum has to be generated and electrons have to be focused to achieve the required power density on the target surface. A second reason is that, especially in the case of thermionic emission, uh, the metallic filament is actually heated to a very high temperature because, as we said, the energy in this case is transferred in the form of heat. And at such high temperatures, metals are susceptible to oxidation and corrosion uh, in the presence of, say, ambient atmosphere. So, while we are heating this filament to such a high temperature, we must ensure that it does not get oxidized. And to prevent this, we maintain a vacuum around this gun. We also have this indicative diagram which shows the regimes of pressure in which the different types of pumps are operating. Rotary pumps typically operate from ambient to 10 to the power minus 2 millibar. Root pumps operate in a similar regime except they cannot operate right from ambient, and that's why often you will see that they are attached in series, as also shown here. Diffusion pumps and turbomolecular pumps operate from 10 to the power minus 2 millibar to low pressures, typically say 10 to the power minus 7 millibar or so. And here we also have a schematic representation of the working principle of these various pumps. For the case of rotary pump, uh, the first cycle is suction, where we see that through this inlet, uh, which is connected to the working region, air is sucked into the pump. Then, based on this spring-loaded lever, transports this air to the interior of the chamber. Then it is further compressed, and because of this compression, pressure builds up on this other valve, which was closed in all of these previous stages. And upon the buildup of sufficient pressure, the air is emitted out from this exhaust valve. Root pump uses a similar mechanism, except that instead of a spring-loaded lever here, we have the presence of lobes, which allows for the transfer of air from a low pressure region to a high pressure region. For in the case of diffusion pump, we have uh, oil, which is typically known as just DP oil or diffusion pump oil, which is heated and vaporized. Upon getting vaporized, the vapor of this oil settles or gets adsorbed onto the surface of air molecules, making them somewhat heavier, and which allows them to be eliminated by the pump. A thermomolecular pump, on the other hand, uses stator blades and rotor blades to extract air out of the chamber. and a schematic of a typical electron beam gun with the various pumps is shown here on the right. Here we have another schematic of wire-based electron beam additive manufacturing method, where we see how the wire is being fed in a lateral direction, and electron beam is melting the wire and depositing the layers. Some simplified models have been presented here to model the interaction of the uh, material feedstock with the electron beam. And similar to the case of, say, the other wire-based processes that we saw, the metal transfer mode can be, say, in the droplet transfer form, or it can be the wire stubbing form, or it can be the optimum bridge transfer form. Here, typically, the type of mechanism will be judged or can be ascertained based on the height of the molten region of the wire from the target surface, denoted by this parameter h. Now, the various forces which govern the transfer of the droplet or the molten wire to the substrate are given here. They are the gravity force Fg, the electron beam pressure force Fe. This electron beam pressure is because of uh, the momentum that is being transferred from the jet of electrons which are continuously being incident on this molten metal. Fv, which is the metal vapor jet force, because a fraction of the electrons will actually be hitting the substrate, melting the material there, and also vaporizing it. Because of vaporization of metal, uh, there will be a jet force acting on the droplet also. And then surface tension of the film, which will try to continue holding onto this droplet and try to adhere it to the wire only. Now, this balance of forces gives us the critical radius for a droplet, which is given in this expression here for small r. Some of the other parameters in this equation are the wire feeding angle, the surface tension coefficient, atmospheric pressure, the latent heat of vaporization, universal gas constant, the boiling point of base metal, the liquid surface tension, sorry, the liquid surface temperature, and the radius of the filler wire. The critical condition, which helps us decide between droplet transfer and bridge transfer, is whether this height of the droplet from the base metal is greater than or equal to twice the critical radius. The challenges in electron beam based wire additive manufacturing are similar to other wire based additive manufacturing processes, such as there can be the formation of residual stresses and consequent distortion. The distortion is also shown here in this image, whereas we can see the substrate, which was initially a flat plate, has warped or distorted significantly. And this is just the distortion of the build plate. Similar distortion could also have been affected on the built part also, and it may even have been separated from this build plate. And for residual stresses, as we will remember from our previous discussion, they are inevitable for any fusion-based process involving melting and solidification, because the metal tends to expand when it is liquefying, and upon solidification, it tends to contract. Uh, the presence of tensile residual stresses can be highly debilitating to the microstructure of a material, because no microstructure is perfect and there will always be the presence of some micro cracks, and the presence of tensile residual stresses can help in opening up these cracks and their further propagation. If we are able to introduce compressive residual stresses, into a material by techniques such as, say, ball pinning or laser shot pinning or hammering or any other technique, that may be beneficial as it will inhibit further crack propagation. However, they cannot be fully eliminated. Second, the surface finish is not very good, and this is true for most wire-based processes because here the trade-off is that we can have a higher material deposition rate, uh, as well as there are other aspects such as safety is better because metallic powders, as you know, are very dangerous if inhaled and can lead to severe health complications, whereas wire is a cleaner, easier to handle feedstock. Powders can also be explosive for certain materials because of their high specific surface areas, which can accumulate charge, which is not the case with wires. However, because of this high deposition rate, the surface finish for a wire-based part when deposited is also very bad. As we can see here, the surface finish for this part given in the example, the layers, individual layers can be discerned by naked eyes. If we are building any part with overhanging features, then support materials cannot be easily removed if they are added. So typically by using these processes, while using these processes, we'll either stick to say simple geometries or we'll make use of some multi-degree of freedom kinematics, either using say a 5-axis or 3-axis table or a robotic arm. Uh, Another challenge is the evaporation of alloying element material because the nominal composition of the wire that we are starting with may have a specified composition for the grade of alloy that we are say willing to deposit. But because of the high temperatures that the material is subjected to because of the action of the or because of interaction with the electron beam, not only will it get melted, the temperatures can reach sufficiently high levels to start evaporation of some of the components, especially the low temperature uh, alloying solutes. And so the final composition that we get in the deposited part can be significantly different from the nominal alloy composition. And of course, just like the other wire-based AM processes that we discussed, lack of omnidirectionality can be a concern if the wire is being fed laterally from one direction, because just like we discussed last week, depending on the relative motion of the electron beam and the wire feeding apparatus, uh, we can have different feeding characteristics. It can go from back feeding to side feeding to front feeding, which can lead to a lack of omnidirectionality and a consequent lack of isotropy in the material properties. Some of the ways to counteract or balance out these negative effects are by dynamic adjustment of the substrate to maintain omnidirectionality, or rotation of the substrate to maintain consistency between orientation vectors has been successfully commercialized with CRT. And an interesting feature which can be further exploited is that the electron beam which is used to deposit this material, if say emitted at a low power, can be used for metallurgical analysis of the build part, because even while doing this metallurgical characterization by using electron microscopy techniques, we essentially bombard the surface of a material with a beam of electrons. It's just that we ensure that they do not damage the surface. And so, even in the case of this electron beam AM processes, the beam of electrons is already available with us. If only we can modulate the power and ensure that it is suitably low to not damage the material or melt it, then we can also perform some metallurgical characterization, such as electron microscopy or elemental distribution or others. The issue of omnidirectionality is especially relevant, and it can be solved by the use of coaxial feedstock surrounded by the fusion source, where a centrally fed feedstock surrounded by multiple equally spaced oscillating electron beams can be used. Why oscillating? In this example here, what we can see is that uh, we have this we have these three curtains of energy beams surrounding the material. But what we have in actually is just a single electron beam, which is just being oscillating or deflected very fast within this region. And because of the high speeds, it appears as if it's not a single beam, but a curtain of electron beam, which is acting in that region. And by the use of such multiple equally spaced oscillating electron beams, we can get a heat intensity distribution which is similar to an annular laser beam profile. An alternate technique would be to use a hollow electrode, an example of which is shown on the right here. And as we mentioned, because of the various advantages, such as the high deposition rates, very high deflection speeds of the electron beam wire AM processes, they have already been commercialized and put to use. And NASA is among the first organization which developed a wire-based process and called it solid freeform fabrication. And the images of such a technology are given here. And now we'll discuss the wire-based AM processes utilizing lasers as the energy source. Now, typically when using lasers, we have a dedicated laser unit which will have a chiller, laser generator, and a UPS. Once the laser beam is generated, it is transferred to the deposition head by an optical fiber. The deposition head itself can be mounted onto a multiple degree of freedom robot as shown in this example. A controller is used to control and connect the laser unit with the deposition head and the robot. This dedicated wire feeder is used to control the flow of wire feedstock through pinch rollers, and argon gas is used to provide a protective atmosphere to prevent the influx of atmospheric gases such as oxygen into the molten pool. However, instead of using a robot, sometimes the deposition head can simply be retrofitted onto an existing 3-axis or 5-axis CNC machine. And the schematic for such a system is shown here, where again we have a dedicated laser unit with a laser generator section, a UPS, and a chiller unit to prevent overheating. The laser is transferred to the deposition head using an optical fiber, and the deposition head itself is mounted onto the machining head of a pre-existing 3-axis or 5-axis CNC. Uh, metal metal feedstock delivery unit in the form of a lateral wire feeder is attached to this head, and a dedicated wire feeding system uh, is responsible for transfer of wire feedstock at the required say material deposition rate. And the interface between all of these is controlled using sophisticated controllers. Again, argon gas is used to provide a protective atmosphere around the liquid molten pool. And for the case of laser-based wire additive manufacturing processes, um, as we saw in the example, we can either have the wire feedstock being fed from the side at some pre-specified angle, constituting a case of lateral wire feeding, as shown in this first example here, where the wire is being fed at some angle alpha and at some nominal height h of the nozzle, and the laser head is coming from the above, but it is not exactly vertical. It is inclined at a small angle beta. The reason for this inclination is very clever. It's because if say metals are typically reflective, but if we are working with a highly reflective workpiece or a material which is very highly reflective, such as aluminum, then there is a chance that some of these incident laser beams will be reflected back into the uh, laser optics if it is exactly vertical. That is because the angle of incidence is equal to the angle of reflection. If the incidence is normal to the surface, the reflection will also be normal, and there is a chance of ingress of these reflected laser beams back into the laser optics, which can damage these optics. And as we know, these are very sophisticated, sensitive, and costly systems. So to prevent such damage, it is tilted at a small angle, which does not affect the properties of the printed part, but definitely saves the laser optics. Or if we want to ensure that there is omnidirectionality in our process and the built part has isotropic material properties, we can opt for an omnidirectional wire feeding system, which can be affected either through the use of a rotating feeder, as shown in this first example here, where the wire is still being fed from a side, but now it can also be rotated around the laser axis so that we can maintain a particular feeding direction. Say in this case, in the plane shown, it is a case of front feeding. So if the direction of scanning of the laser changes, the entire feeding assembly can rotate to ensure that front feeding continues. Or we can use an annular beam where we start with a TEM00 beam profile. But by the use of some sophisticated optics, we can split this beam, feed the wire material through this beam, again join them back into a solid or annular shape, and then use it to deposit material. Or a simplified version of this is where we simply split the beam into two or more, say, separate beams, and through the distance created between them, we can feed our material, and then all of these beams are made to converge again onto the substrate surface. Here we have pictures of laser metal wire additive manufacturing subsystems. On the left, we have a deposition head which is mounted onto a robot. It also has a CMOS coaxial camera for monitoring of the melt pool, the laser head, a rotary table, and a lateral wire feeder, which may or may not have omnidirectionality. There's also a second nozzle, which I presume is for the delivery of the inert gas. And on the right here, we have a rotating feeder, which ensures omnidirectionality. However, omnidirectionality may not be needed for all cases, especially if the application is one where we know uh, from before that the feeding need be only in one direction. Such an example is shown here, where we are cladding on the surface of a cylindrical substrate. As this cylinder rotates, this cladding head can deposit material around it in a spiral tool path and can continue moving. Here the deposition direction is fixed. Now, even with a fixed deposition direction, the wire feeding position can be different, and this in turn can have an effect on the isotropic nature of the material properties. So depending on where the wire is getting molded and getting added to the melt pool, it can happen at the leading edge, where the wire is getting molten at the very, say, front edge of the melt pool, or it can happen at the trailing edge, where because of some misalignment or maybe intentionally, we are positioning the wire and the laser in such a relative fashion that the wire is melting near the trailing edge of the melt pool and is getting added near the tail part of the melt pool. However, typically we would want this addition to take place at the center of the melt pool. The reason for it being that typically the region near the center has the highest temperature as well as the deepest, or it is the region with the highest depth as well. So any material addition here can ensure maximum homogenization and complete mixing, and so it is most desirable. We know that typical, say, laser melt pools are not symmetric. So if the laser center is indicated by the red dot here, the melt pool will typically, and it is traveling in the indicated direction. The melt pool will typically be asymmetric, and it will have some molten region ahead of the laser source and a long tail. The flow inside the molten pool will, for most materials, be radially outwards from the laser center. This characteristic can, of course, be affected by the presence of surface active elements or by the variation of the surface tension with temperature, whether it is a positive slope or a negative slope. But typically, for most metals and alloy, this is how it will be. Similarly, when we are changing the moving direction or by changing the relative orientation of the lateral wire feeder with the moving deposition head, such properties can be affected. As we discussed, the beam can also be split, or from a TEM00 profile, we can affect a donut profile where there is a hollow region in between. And this is done by the use of sophisticated optics called axicon, which is used, which uses a prism-like, say, material as shown here, prism 1, to split the incident beam into multiple beams. From the gap which is formed between these beams, the wire can be fed, and then by the use of a second suitable prism, these separated or discrete beams can again be converged onto the substrate surface to melt the wire feedstock. And this has been commercialized by Precitech as shown here. A second system, which is maybe a simplification of this one, and comes with much simpler optics and consequently, I presume, a lower cost, is that where instead of having a donut shaped beam profile, we just split the beam into several discrete beams and then join them together onto the substrate surface using mirrors, which we saw in the video courtesy of Fraunhofer. Now, in any laser-based metal wire additive manufacturing process, there are a large number of independent variables which can affect the property of the material. Most of them are listed here. In terms of the variables which dictate or control or govern the thermal energy, we have the power of the laser beam, the beam diameter, the beam profile, working distance, and wavelength. However, despite all of them being variable, once we have, say, purchased or developed a machine, we will not always want to vary all of them, or sometimes it may not always be possible also. For instance, for most laser systems, the beam profile and wavelength and the beam diameter may be fixed. Beam diameter we may still be able to play with, but the wavelength and profile will mostly be fixed. The working distance is something which we can vary, but typically, say, we will have an optimum working distance which we could have arrived at, and we will not want to change it much. Apart from academic curiosity, where we would want to check or investigate the effect of, say, increasing or decreasing this working distance, leading to various forms of defocusing. But in a typical print, the parameter which will be varying is the power, which will be varying the thermal energy input to the material. In terms of the variables controlling the feeding rate, we have the feeding direction, the feeding position, the feeding angle, the wire feed rate, and the gas flow rate. Again, once we have, say, if we have a coaxial wire feeder, then the direction, position, and angle are all fixed. And if we have a rotational type lateral wire feeder, even then the angle and the position are fixed. It's only the direction which you are varying. The gas flow rate also, typically we would want to maintain a sufficiently high flow rate. Typically, say this will be in the range of 10 liter per minute to 30 liters per minute, depending on your chamber size, the material you are working with, the amount of atmospheric control that you need, similar factors. And it will not really be varied again out apart from academic curiosity, where we can vary the gas flow rate or the gas flow type and the gas type and check what effects it will have. And typically the variable which we'll be working with to change the feeding characteristics is the wire feed rate. In the case of material and design parameters, we will of course change the material of the wire. The diameter of the wire again is limited to a few standard numbers. It's because those are the commonly used welding wires available to us, say typically between 0.8 to 1.2 millimeters. The material of the substrate, but then this is like a design parameter which will already be given to us for a given application. Substrate geometry is typically flat, and feature geometry will again be as given to us. And in terms of motion and path, again, the various variables are the scan speed, the track overlap ratio, the deposition path, interpass time, and the preheating temperature. Again, based on our optimization process for a typical machine, material, and parameter combination, we would already have optimized the track overlap ratio, the step over distance, the deposition path, the interpass time for single beads, then for multiple tracks in a single layer, then for many single tracks built on one on top of the other to form thin wall like structure, and then finally for a 3D part. And typically we'll be varying only the scan speed to control the material deposition rate and the energy deposition rate. An interesting feature or interesting variable which you see here is the preheating temperature. And this can prove especially useful because when we are depositing any molten material, typically it will be uh, uh, at some superheat, or in the critical case, we can assume that okay, at least it will be at the liquidus temperature. Compare that to the temperature of the substrate will be at, which will be at the ambient temperature, say 24 degrees Celsius, and the metal will be at some 1400 degrees Celsius, which presents a very large thermal gradient for the metal. And these large thermal gradients again can result in residual stresses. By preheating the substrate to some pre-decided temperatures, say 200 or 300 degrees Celsius, we can reduce the amount of or the magnitude of thermal gradient, which can prevent or mitigate the formation of residual stresses or at least moderate them. Secondly, we may be working with materials such as aluminum or copper, which are notoriously difficult to print with such laser-based techniques. By preheating them, this may be because of the high reflectivity or the poor absorptivity of these materials. But by preheating them, we can overcome these features. That is, say, with increasing temperature, we can make them more absorptive, and so it may improve the print quality. In this slide, we have some typical numbers for the various variables used in a laser metal wire additive manufacturing process. The typical types of lasers that are used are the solid state diode lasers, disk lasers, ND arc lasers, fiber lasers, and CO2 lasers, even though they are mentioned here, they are not really used much with metals. In fact, they are more suitable for ceramics. And the reason, as I believe we have discussed previously, is because of their wavelength and how this wavelength interacts with the material. So, for the case of CO2 lasers, the wavelength is typically, say, of the order of 10,000 micrometers, whereas for diode lasers, this is typically of the order of, say, 1,000 micrometers, like 970 or 1070 micrometer or so. Uh, it is not uncommon to see laser powers between 1 to 20 kilowatts. For instance, for the laser metal wire AM machine that we have here at IIT Bombay, it has 3 kilowatt peak power. The deposition rates can be between 1 to 50 grams per minute, which is significant and highlights the commercial viability and high deposition rate of this technology. Layer thicknesses will typically be of the order of 1000 micrometer or more. Wire diameters are typically from zero point 0.2 to 1.2 millimeter. However, in practice, this number will be more between, not even between, we will have say options of zero point 0.8, 1 and 1.2 mm. Recently, I also saw a paper using a zero point 0.9 mm wire. The typical bead width, which will be achieved in this process, will be from 5 to 15 times the wire diameter. Surface finish which is obtained in the as-built condition is between 40 to 60 micrometer. Uh, Center line average roughness values. For reference, a mirror finish is said to be 1 micrometer RA. So we can imagine the type of finish that we are getting. The travel speed of the laser can be between 500 to 2400 millimeters per minute. And apart from cladding, some of the other applications which this technology has been put to include surface protection, uh, the addition of features on existing geometries, repair of broken geometry, and surface treatment. Now, it is important to understand the wire deposition characteristics based on the interplay of the laser power, the scan speed, and the wire feed. And this deposition characteristic can be of three types. It can be wire dripping or droplet transfer type, an example of which is shown here on the bottom left. And it occurs when the available energy is too high. Because of this very high energy intensity, the wire tip is melted much before it can uh, reach the center of the melt pool or the desirable region of deposition. This high energy intensity locally is achieved usually when the wire feed rate is excessively low, assuming that the transfer speed and laser power are fixed, or if the laser power and transfers and the feed rate are fixed, then it can happen because of very low traverse speed and results in discontinuous tracks where we have regions of high deposition, which we see in the form of these bulging features, and low deposition, which we may see as a form of valleys or even in some cases lack of deposition. Whereas there's this small region in the center which appears to show almost uniform deposition. The polar opposite case is that of wire stubbing, where the available energy locally is low and hence wire enters the melt pool in a nearly solid form, resulting in the collision of the wire tip with the solid substrate at the base of the melt pool. This makes the wire tip move away from the center of the melt pool and can lead to features such as I am highlighting in the image. It's not like the wire will remain entirely solid. In fact, most of it will melt away by the energy in the melt pool and it will solidify as tracks with irregular shape. And this can occur when the wire feed rate is too high, assuming the power and traverse speed are fixed, or if the wire feed rate and power are fixed, it can happen if the traverse speed is too high, or if both wire feed rate and speed are fixed, this can result from low deposition powers. The optimum case which you want to achieve is that of bridge transfer or smooth wire transfer, which is the most desirable metal transfer condition observed when the available energy is sufficient enough to melt the wire tip at a point close to the intersection of within the melt pool. And this results in uniform and really neat tracks as shown in the figure. But what are the quantitative parameters based on which we can say distinguish or predict these deposition characteristics? Those are energy density, typically in the form of linear energy density, shown here in EL, and the deposition volume per unit length of track pass. Energy per unit length of track has the units of joule per ml and is given as power by traverse speed. Power will have units of watt, so joule per second, and traverse speed will have units typically of say millimeter per second, and so these will have the units of joule per millimeter, as we already saw. The deposition volume per unit length of track pass will have the units of millimeter cube per meter, which has the traverse speed and the wire feed rate as the determining variables. We have A into VW by VT, where A is the cross-sectional area of the wire in millimeter square. So the units here will be millimeter square into millimeter per second by millimeter per second, which gives us the unit of millimeter cube per millimeter. And based on a large number of experimental trials or data available in the reported literature, we can come up with such processing windows where we can distinguish based on the energy per unit length of track and the wire deposition volume per unit length of track, whether say a given set of processing conditions that we are targeting will fall in the dripping region, probable dripping region, smooth wire flow region, probable stubbing or stubbing region. And we also have this very useful equation for critical power, uh, which relates the critical power efficiency eta, wire diameter dw, velocity of feed wire, specific heat of the material, melting temperature, ambient temperature or preheat temperature, latent heat of melting, laser spot size, depth of penetration, and speed of cladding head. And here they are say divided into these two terms. Because the first term relates to the energy required for melting the wire, and the second for energy required to for formation of the melt pool on the substrate. Again, in the case of dissimilar deposition, both of these materials can have different properties, and even then, the properties themselves can, or they are mostly temperature dependent. And so, for accurate estimation of the critical power needed to affect such a deposition, uh, this represents the necessary energy balance. Now, notice how the efficiency eta has value of the order of 70%, which shows how this is a really energy efficient process with almost 100% catchment efficiency and almost very high or near total utilization of the energy input to the system. Uh, Towards the end of this week, Professor Kapil also started discussing powder-based additive manufacturing processes. And the topics which will be looked at are the classification of powder AM, introduction to powder feed AM, Classification of powder feed AM, powder handling systems, that is metering and conveying systems as well as delivery systems, and some of the popular machines which are commercialized. Now, powder-based additive manufacturing can either be of the powder bed type, where the powder is already available to us in reservoirs, and a thin layer of it, is spread onto the printing region by the use of rollers, and then this region is scanned with an energy beam, or some binder is deposited in the regions to be printed. Or it can be the powder feed type, where the powder is not available already on the printing substrate or the pre-deposited layer. Rather, it is fed or brought in contact with the laser. That is, it is delivered by some carrier gas. Now, for the powder bed AM processes, it can either be binder-based powder bed AM, as we just discussed, or it can be energy beam-based powder bed AM. Among the energy beams, we can have laser beam powder bed AM or electron beam powder bed AM, depending on the fusion mechanism, whether it is solid state or liquid state. If it is solid state, the process is called selective laser sintering, because they are only sintering the metal powders and not melting them completely. Or it can be selective laser melting, where melting, fusion, and solidification takes place. Now, directed energy deposition is one of the most common names used to allude to such processes, but it is far from the only term used. Some of the other commonly used and reported terms are direct laser deposition, or DLD, laser consolidation, or LC, laser engineered net shaping or lens, which is a trademark of Optomed, direct metal deposition, or DMD, or 3D laser cladding. Just like all other AM processes that we have been studying, this also has the various cycles, those being the pre-processing, build process, in situ processing, and post-processing cycles. In situ process cycles, as we were discussing last week, are those where we introduce, say, an additional machining step, or a forming step, or some laser shot peening or ball peening step to improve the material properties of the deposited layer. And this can be done either layer by layer, or it can be done for the entire part as well, depending on the requirement. Say if it's a machining process, we can machine each layer to maintain their height accuracy, or we can machine at the end for a hybrid process to achieve the desired geometry or surface finish. The build process typically involves the steps of creation of a small melt pool by the use of a highly focused heat source, the injection of build material, either in the form of powder or wire, into this melt pool, and the generation of synchronized motion of heat source, material injection, and substrate to develop the desired part geometry. Let us briefly discuss the working principle of powder feed based AM process. A typical powder feed system uses a high power laser, uh, up to 10 kilowatts, but in practice, typically these powers will be 1000 watts or lower. A focused laser beam falls on a substrate and creates a molten pool. In this molten pool, powder material is injected to get melted and deposited. This process is called as laser cladding. Relative motion is provided between the substrate and the laser beam so that the deposition can be done along the desired path. Inert shout gas such as argon, helium, or in some cases even nitrogen may be used to shield the melt from atmospheric oxygen. This feature also improves layer to layer adhesion by providing better surface wetting. The part is built onto an XY table placed below the deposition so that the laser powder head can move on it in a raster fashion to selectively deposit the material. After a single layer is built, the distance between the laser beam and the substrate is increased by the desired layer thickness. For powder feed based AM processes, typically this will be of the order of tens to hundreds of micrometers. And while fabricating features or assembly components requiring deposition in planar layers at angled orientation to the parent or base feature, the laser beam powder delivery head can be tilted using either a 5-axis CNC machine or a robotic arm so that the beam axis is normal to the deposition plane. And this is highly useful when producing overhanging features without support mechanism. This principle is also illustrated here, where we have a laser, a powder delivery system where the metallic powder particles are deposited by delivered by a carrier gas, and the resulting clad, which is being developed. Laser cladding was originally developed for the surface treatment of parts with a view to improve their wear properties or corrosion behavior, and the process aimed to clad a new material onto part surface with minimum dilution of the substrate. And it was introduced by Professor William Steen. Typically, the powder is carried by argon gas for delivery towards the molten pool created by a laser beam. Therefore, this technology is not compatible with electron beam. Let us discuss why that is so. As we saw, for the case of electron beam based wire additive manufacturing processes, uh, to ensure that the beam of electrons reached the target surface and could deliver energy to it for melting, fusion, and deposition of the metal, we had to ensure uninhibited and direct path of the electrons to this target surface. For this, we ensured a vacuum in the working region to ensure that no heavy molecules or no other heavy particles could be encountered in the path of the electrons. However, here the metal particles or the metal powders are carried by some carrier gas, typically argon. If argon is introduced into the working chamber of an electron beam system, the vacuum will be lost, and thus the electrons will get deflected much before they can reach the target surface and result in printing. Thus, this technology is not compatible with electron beam. The present slide highlights the architecture of a typical DAD machine, where we have powder metering units, which control the quantity as well as the composition of powder in case we are trying to alloy multiple powders together. The mixing chamber, where these powders can be mixed together in well-defined proportions. The powder conveyance, which uses some inert gas, typically argon. The powder delivery and optics, through which this powder is deposited onto the target surface. A shielding gas, which is used to say protect the molten pool from atmospheric oxygen. Typically, this will be same as the powder delivery gas, and a control interface to sync the functioning of all of these different subsystems. And the powder handling system for powder feed AM can be categorized into three separate phases, which are powder metering units, powdering, powder conveyance units, and powder delivery units. Metering can be done by aspirating or using some screw or roger mechanism, a feeder wheel, or by electrostatic methods. Conveyance can be achieved either by mechanical or pneumatic means, and among the mechanical methods we have the use of vibration, screw, and gravity chutes, which are well reported. And the delivery of this metal powder can be gas assisted, vibration assisted, or simply gravity driven. Here we have a schematic diagram of the screw or auger-based method, uh, which was among the first ones to be developed and suggested. The design of such a system consists of a motor-driven screw which pushes a specified or desired amount of powder into the chamber where it can be picked up by the inert gas and carried forward. The quantification of this specified amount of powder can be done based on the setup dimension and the RPM of the screw. On the right, where we have a system for mixing two powders, powders 1 and 2, each with their own auger screw and drive motors. And then, based on, say, relative RPM and relative dimensions of the two, we can introduce a fixed proportion of each of these powders into the stirring chamber for mixing and further usage. This metering and convening can be done by vibratory methods, which are typically encountered in agriculture and food processing industry. But in the case of metal additive manufacturing, their usage has mostly been exploratory. Here we have two examples where the combination of voice coil vibrator for longitudinal vibrations and radial vibration uh, by the use of piezoelectric ring can be used to transfer metal powder from a hopper to the substrate, or by using vibrators again for alloying of two powders inside a mixing vessel. Gravity-based methods have also been reported, which are similar to vibratory methods and are rare for commercial applications. And one of the major hurdles which limits their application is the phenomenon of jamming of powders in these gravity-based systems. Jamming stops the granular flow for systems operating under gravity by forming arch-like structures with the particles. And it has been reported that if the diameter of the conveyance pipe is capital D and the diameter of the powder particles is small d, if the diameter capital D is smaller than or the order of 3 to 4 the diameter of the powder particle, such jamming phenomenon can be encountered very frequently, and so the diameter of the convening pipe should necessarily be greater than 3 to 4 times the powder particle diameter. Of course, the powder particle diameter is never available as just a single value, but rather as a distribution, which will have some mean, minimum and maximum values. Uh, a more common and commercially used method for powder metering and convening is actually one which uses pneumatic principles. And out of all the methods, pneumatic powder feeders are most popular for powder feed AM and laser surface flattening setups. All commercially sold powder feed AM units employ this mechanism for powder metering, conveyance, and delivery. Pneumatic methods work by creating a pressure difference within a system which facilitates metering and conveyance of powder feedstock. A schematic of this is shown here, which is developed exclusively for the DED process. We have a base plate which has one hole, which I am currently hatching in blue, and on top of it we have this index plate which has many holes. Uh, the index plate rotates at some fixed angular velocity, and depending on the angular velocity, one of these holes of the index plate will align with the hole in the base plate. Through the hole in the base plate, compressed inert gas is allowed, uh, which is then channelized uh, into the powder outlet. And thus, depending on the velocity of the index plate, the angular velocity of the index plate, and the rotational position between the index plate and the base plate, the requisite amount of powder can be allowed to leave the powder hopper. And this is because we are introducing a high pressure gas through the hole in the base plate, whereas the pressure inside the hopper will be comparatively lower. And so because of this pressure difference and pneumatic effect, the powder can be delivered. So the other designs based on pneumatic principles are also discussed. However, they are not really put to commercial usage. We have a design which uses a rotating disc fixed to or attached on top of a fixed disc, which has a groove and a vacuum line, and another system where we have a hopper with some valve and metering wheel, where a carrier gas can be used to deliver the powder. Electrostatic methods have also been reported, where electrostatic forces are used to control valves, which then retard the free flow of particles. However, this system is very sensitive towards the particles' electrical conductivity, and clustered particles adhering onto the glass wall reduce the diameter of flow column, thereby reducing the flow. Say, for the present example, if the electrodes in this region are suddenly activated, this will lead to accumulation of powder particles affected by the electrostatic field of these electrodes. They will tend to get accumulated in this local region and thus clog or jam the feeder pipe. Now, once this path is constrained, it will disallow the further movement of granular flow of powder particles, thereby preventing the conveyance of powders. Thus, the electric signals can be modulated to deliver the metal powder. The powder delivery nozzle for a directed energy deposition system can be classified into various types as shown here. It can be a lateral feed or off-axis nozzle as shown in figure A, where the powder is being fed from one side and the laser comes from the axial direction. It can be of a continuous coaxial type, where the laser is still coming from the center and the powder is being fed from the sides or from all sides radially in a continuous fashion. This continuous coaxial configuration can be approximated into a discrete coaxial configuration, where instead of, say, a completely conical coaxial channel, we have these multiple discrete channels through which powder is fed. Or instead of having the laser come out from the axial direction and powder from all around, we can do the reverse, where we have the powder being fed from the center and the laser surrounds it from all directions, which is a central feed with annular laser as shown in figure D here. And just like the previous case, this can also be approximated by a central feed with discrete laser system. Some of the advantages of the off-axis nozzle are discussed here, where the feeding of powder oblique to the heat source facilitates easy setup design. Laser feed nozzles create an asymmetry in powder temperature, laser intensity, and the resulting melt pool, which must be accounted for when, say, using this for some targeted application. To avoid anisotropy in powder feed AM parts and to achieve higher dimensional accuracy, coaxial nozzles are preferred over lateral feed nozzles. However, such off-axis nozzles may still be preferred for cladding of cylindrical components on a rotary setup, similar to the off-axis or lateral wire feeding system that we saw previously. In the design of continuous coaxial nozzles, we can have several ports for entry of the shield gas, and each of these will serve different purposes. Uh, the shield gas is purged to protect the laser optics from metal fumes and dust. It also serves as passageway for convergent powder stream and is also acting as the shroud gas for protecting the melt pool from atmospheric gases such as oxygen. In this case, the inert gas entering from the top shown using red arrows, actually serves to protect the laser optics. Uh, the one shown in blue is responsible for delivery of powder, as we can clearly see. And the path of the inert gas, highlighted by green arrows, is useful for protecting or displacing the atmospheric oxygen and preventing the molten pool. Now, the other popular designs, which have also been tested out, are shown in this slide here. For instance, we have this design which uses the shield gas or a blanket of shield gas to protect the laser optics from any, say, deflected powder particle or metallic fumes or laser beams which may be coming into the system. This shield gas is transparent to the laser wavelength, but it will prevent the backflow of metallic powder or fumes. Now to discuss the discrete coaxial nozzle designs. Discrete coaxial nozzles typically use multiple, such as 3 or 4 jets of powder stream, delivering feedstock directly to the melt pool via separate and distinct powder delivery channels. The inclination of these channels with respect to each other affects powder flow characteristics and shifts the location of powder stream's focal point relative to the laser beam. The number of powder streams or channels that are participating has a significant influence on the stream characteristics and the catchment efficiency. And it has been shown by studies that with increase in powder channels, the particle velocity in each of the delivery streams will reduce. This reduction in particle velocity produces increased clad area, a higher catchment efficiency for the same process parameters. Uh, this is what was discussed in this week, and now we'll just break for a short while, and when we come back, I will discuss example problems that will be useful for solving the assignments. Good evening and welcome back. Let us now look at a few example problems from the contents that were discussed in this week. The first question is asking us, which are the deciding factors in choosing optimum standoff distance in a blown powder AD process? Um, is it A, that the focal point should be sufficiently away to prevent nozzle damage? B, that the laser working zone should fall within the standoff distance? C, the laser focal point or the waste radius should fall within the standoff distance, or a combination of these. Should the focal point be sufficiently away to prevent nozzle damage? We know that in the case of blown powder DD process, this is nozzle and the substrate, and the distance between them is typically called the standoff distance. Now, in this case, since you are working with metals and lasers, very high temperatures, say easily 1700, say 1000 Kelvin or so, can be very easily achieved. And so, if the nozzle is very close to the substrate where this melting and fusion is happening, it can sustain uh, thermal damage. And so, it should be sufficiently away. Another way to think about this is that we saw how during deposition, if the process is not optimized or unstable, we can have regions of varying deposition heights. And so if the nozzle is very close to the substrate, it may even end up colliding with the irregular features. And so the focal point should be sufficiently away to prevent nozzle damage. The laser working zone should fall within the standoff distance, of course, because this laser working zone can be loosely defined as the region where the laser interacts with the metal powder. Of course, it should be within the standoff distance because if this interaction region is say into the substrate or somewhere else, then you will not obtain deposition as desired. Should the laser focal point or waste radius always fall within the standoff distance? In fact, we have also seen examples where this waste radius was in fact within the nozzle itself. And so it is not absolutely essential for this to fall within the standoff distance. And so option D is the correct option. Question 2 is asking us, what are the reasons for difficulty in additive manufacturing of metals like copper and aluminum? Is it the high reflectivity? Is it high thermal conductivity? Is it that laser of suitable wavelengths are not available? Or is it a combination of some of these? We have discussed some of these points before, so it may be easy to answer. We know that both copper and aluminum typically have very high reflectivity, which means that most of the laser energy which is incident on them actually gets reflected away. They also have very high thermal conductivity, and so what happens is rather than localized melting, the heat is conducted away very quickly, leading to an overall rise in temperature in the entire bulk of, say, the substrate or pre-deposited part, but not localized melting. And we also saw that typically the lasers that we use for such processes may have wavelengths around 1000 micrometer. That is, they might be in the infrared range. However, they are not always suitable as they do not interact very well with copper and aluminum. For copper, for instance, blue or green lasers have been found to be more suitable because of their shorter wavelengths, uh, which interact better with copper. So the suitable wavelength lasers are available and they are becoming increasingly common. This is not viable So option D is the correct option. What is the drawback of utilizing a central feed with annular laser as a powder delivery system? Is it the need of sophisticated optical systems? Is it low catchment efficiency? Is it lack of fusion at the edge of the melt pool? Or is it lack of fusion at the center of the melt pool? Sophisticated optical systems are of course needed, as we saw. The catchment efficiency is actually very high because the powder is being fed centrally. So option B is not correct. Uh, the lack of fusion at the edges of the melt pool is typically characteristic of lateral feeding of powder, where there is an imbalance in the power available locally or the energy available locally and the amount of material being deposited. Whereas in the case of central feed with annular laser, this will be alleviated. And similarly, there will not be a lack of fusion at the center of the melt pool because, say, even if we imagine that our annular laser has, say, some configuration like this, where the powder is coming in from the center and the laser is coming from the sides here. As a continuous curtain, so to say. If I took various sections uh, and saw what the laser looked like, so say here it may have this donut-like profile, but it will keep on converging. And it is entirely possible that after a distance, it will have a TM00 similar profile. And irrespective of that, because of the conduction of heat, uh, uh, there will not be a lack of fusion at the center. And typically, as we know, the center is the region with the highest temperature in the melt pool. So option A is correct. Question 4 says that a student proposes the idea of blown powder direct energy deposition using an electron beam as the energy source. What advantage will this technology provide over laser-based blown powder directed energy deposition? Is it the lower cost of the proposed idea, higher production speeds, lower porosity of finished parts, or none of the above? We discussed something similar, how blown powder directed energy deposition and electron beam energy source are not really compatible with each other. The reason for this being because of the very lightweight and the very low mass of electron particles. They can be accelerated to great speeds and can transfer a large amount of momentum. But because of being so light, if while traveling they encounter some heavy molecules or heavy particles, they can be very easily deflected. So, to ensure printing or a targeted delivery of energy to a target surface, we have to ensure that these electrons travel in the path as say designed. And to ensure this, we have to remove all the heavy molecules or heavy particles from the working region. This is why a vacuum is needed, typically of the order of 10 to the power minus 5 millibar in the working chamber and 10 to the power minus 9 to 10 to the power minus 10 millibar in the gun chamber. However, if we use a blown powder DD setup, it will have some carrier gas, say typically argon, which will be used to carry and deliver the powder into the system. But the introduction of this argon will lead to a loss of vacuum. And so this idea is not really feasible. Why are off-axis nozzles preferred for cladding of cylindrical components on a rotary setup. And we saw two examples of this. One for a wire-based AM process and the other for a powder-based AM process. Is it because of the lower cost? Is it because of the higher production speeds? Is it because the deposition is occurring only in one direction? Or is it all of the above? The deposition is definitely occurring in only one direction, which makes the use of off-axis nozzles simpler and more efficient. The production speeds need not necessarily be higher, and the costs may be expected to be lower. But if we are to give only one answer, it will be that the deposition is occurring only in one direction, which facilitates the use of off-axis nozzles. With the increased commercialization and development of new technologies, the difference in cost between an off-axis nozzle and say a coaxial nozzle or discrete coaxial or even say other types of nozzles may not be very large. But the definitive advantage is that the deposition is occurring in only one direction, so a front feeding type configuration may be suitable. Question 6 is asking us, why are inert gases such as argon used in powder feed additive manufacturing process? What uses do they serve? Do they shield the melt pool from atmospheric gases such as oxygen? Yes, they do. Do they deliver the powder feedstock to the melt pool? This is also correct. Do they improve interlayer adhesion by improving surface wetting properties? This is also something that we read and came across in the slide. And do they protect the laser optics? Yes, they do. We saw an example where a blanket of this inert gas was used to shield the laser optics from any incoming powder particles or fumes. And so here, all the four options are correct. Question 7 is asking us, what problems can be introduced by the use of inert gas for shielding the melt pool? Can it lead to the entrapment of gases? Can it lead to turbulence in the molten liquid of the melt pool? Can it lead to porosity of the printed part? Or is it all of the above? Since the inert gas is purged into the system at considerable volumetric flow rates, a typical number for which, as you saw, was between 10 to 30 liters per minute. Entrapment of gases can, of course, be expected, also because the solubility of gases in liquid metal is much higher than in solid metal. This also leads to porosity in the parts because the gases are taken up or dissolved when the metal is molten, but as it solidifies, the solubility of gas in solid metal is considerably lower, and so these gases are liberated, leaving behind pores. And because of the interaction of these, inert gases with the free surface of the molten pool, significant turbulence or surface waves or surface distortions can be introduced into the melt pool. And so all of the above options are correct. Question 8 is asking us, why are wires with diameter less than 0.2 mm not preferred in laser-based metal wire AM? Is it to obtain sufficiently high deposition rates? Is it to ensure that the feedstock wire travels into the molten pool? Is it to ensure that wire does not melt prematurely above the laser focus? Or is it some combination of the above? Now, we have been espousing how the advantage of wire-based AM processes is in the high deposition rate. And if we use a very low diameter wire, the deposition rate for using a wire of very small diameter will not be appreciably higher than using, say, high deposition rate with powder. And thus, we necessarily want to use wire which is of relatively good size, say typically between 0.8 to 1.2 mm. Is it also to ensure the motion of feedstock wire into the molten pool? As we have previously discussed, the wire is typically available in the form of a spool, from which it is fed into the nozzle using pinch rollers and other mechanisms which we saw for FDM. Now, this will have some pre-existing tension because of being coiled in the spool. And if the wire is very slender, or that is to say, if it has a very small diameter, it can bend easily and can have high curvatures. And thus, instead of entering into the melt pool, it can bend away. Of course, the figure which I am showing is exaggerated, but you get the idea. However, to prevent premature melting of wire above the laser focus, we can simply adjust, say, the standoff distance or maybe some of the other process parameters to correct this. Both A and B are the correct options. And question 9 is actually a numerical question, but seeing how I think currently there are no participants in the group, I will save this for next week, where I can discuss it with some of the other participants and we may all benefit from it. It's almost the end of the session. So I thank you for tuning in to week 9 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. I am Sourav Goswami from IIT Bombay, and I hope to see you again next week. Thank you very much.